Hello, guys. Welcome to exam practice test number 4. I'll just go through the problems and solutions really quick. I apologize for this coming later. I ought to have done this long ago. Let me make this bigger. Okay. So right here we have the first problem. Let me make this little. So it says 2 slits separated by 2 times 10 to the minus 5 meters are illuminated by light of wavelength 625 nanometers. If the screen is 6 meters from the slits, what is the distance between the m equals 0 and m equals 1 bright fringes? So the condition for the first order bright fringe is known to be d sine theta 1 equals 1 alpha or lambda, sorry, for the wavelength. So theta 1 is sine inverse of lambda over d. So sine inverse of lambda, the wavelength, which is given 625 nanometers, you convert to SI units times 10 to the minus 9 divided by the slit distance d, the 2 times 10 to the minus 5, the separation of the slit. So that gives us theta 1. So the distance between the m equals 0 and m equals 1 fringe is going to be L tan theta, which is 6, the screen, tan the theta you just got, tan 1.8 degrees, and that gives us this 18.8 centimeter answer here. Okay. So first of all, you find theta 1 corresponding to the first order bright fringe, and then you put it as theta y over L is tan theta, and then theta y, the distance between m equals 0 and m equals 1 becomes the L tan theta, and the L is given to be the screen, the distance of the screen from the slits. Okay. Now we go to the second problem. Which one of the following statement best explains why the diffraction of sound is more apparent than the diffraction of light under most circumstances? And the correct answer here is E. The wavelength of light is considerably smaller than the wavelength of sound. And that is why the diffraction of sound is more apparent, because they can easily see the bending around the diffraction grids or slits compared to smaller wavelength that the bendings are almost not observed as much. Problem 3 says a spy satellite is in orbit at a distance of 1 times 10 to the 6 meters above the ground. It carries a telescope that can resolve the 2 rails of a railroad track that are 1.4 meters apart using light of wavelength 600 nanometers. Which one of the following statements best describes the diameter of the lens in the telescope? So we're going to use the small angle approximation. So usually this is tan theta equals y over L, theta y over L that we did the last example. But here in the small angle approximation, tan theta equals theta. So for the small angle approximation, I can write here tan theta is approximately equal. So I'll put the approximately equal sign here so you see what's going on. All right, here it's approximately equals theta, which is y over L. So y is 1.4 meters divided by L, the distance right here between that is above the ground. And then that's going to give us this angle. So theta is 1.22 lambda over d. Then from here, we'll get d is 1.22 lambda over theta. Becomes 1.22 times the wavelength, 600 nanometers, converted to SI units over theta we just got here. So this is how you get the theta, the distance for this one, the d, the diameter of the lens of the telescope. So it's 5.5228, so it's greater than 0.52. That's the correct answer in the terms of which the options were given. Okay, so problem 4, Leah is moving in a spaceship at constant velocity away from a group of stars somewhere in space. Which one of the following statements indicates a method by which she can determine her absolute velocity through space? She cannot determine her absolute velocity because she cannot perform any measurements to determine this quantity. So except you have a frame of reference. So she doesn't have a frame of reference. So like us on Earth, we have a frame of reference, which is Earth, then we can be able probably measure her from wherever she is. But she and herself in space, she doesn't have any frame of reference. It would be hard for her to do that. So the correct answer is A for this case. Number 5, in the year 2100, an astronaut wears an antique but accurate quartz wristwatch on a journey at a speed of 2 times 10 to the 8 meters per second. According to mission control in Houston, the trip lasts 14 hours. How long was the trip as measured on the watch? So looking at the proper time measured by the watch on the moving frame is the measured time divided by lambda. Lambda is the Lorentz factor, if you like, or Lorentz constant, which is 1 over 1 minus v squared over c squared. So The time you're given is 14 hours, convert to seconds times 60 divided by 1 over 1 minus the speed it's moving squared divided by speed of light squared. So if you do all that math and divide this by 1 over that, 1 over this gives this, then 400 divided by that, you get the answer in seconds, then you divide by 60 and another 60, so you divide by 3600 basically, and you get 10.43 hours. So these seconds divided by 3600 is what gives you this in hours back for the correct answer for that. So we'll go to number 6. It says a spaceship leaves our solar system at a constant speed of 0.920 c. C is the speed of light, so 0.920 times speed of light, and travels to a point in the Andromeda galaxy. According to astronomers in an inertial frame of reference on Earth, the distance to the galaxy is 2.081 times 10 to the 22 meters. What distance does this crew ship measure on its journey? So we're looking for proper distance again. Is the distance the proper distance they measure on the moving frame is the distance measured on Earth that we know divided by lambda again. This is d over gamma. I keep missing. This is gamma. I keep misplacing gamma lambdas. So this is gamma, not lambda. Lambda is the one that's like upside down. So it's d over gamma for the Lorentz constant. So this is 1 over 1 minus v squared over c squared. So the velocity is 0.920 times speed of light squared divided by speed of light squared. So speed of light squared will cancel out. I only have 1 minus the square of 0.92 on the denominator here. And I keep the distance we measure on Earth here in the frame of reference. And then from here, we calculate the distance they measure to be this, which is a little less than the one we measure on Earth. Length contraction, basically. And then, let me see right here. At this point, we go straight to, let me make sure this is recording fine. Okay, at this point now, we go to the next example here. And right here, what we have is example 7. It says the temperature of a 5 kilogram lead brick is increased by 525 degrees Celsius. If the specific capacity of lead is that, what is the increase in mass of the lead brick when it has reached a finite temperature? So classically, we don't observe the increase in mass. Well, if we use relativistic measurement, so the quantity of heat is mc times the temperature change, which is given by this, mass times specific capacity times the c. In this case, is specific capacity, not speed of light. Then after getting this, we can convert this energy to mass using Einstein's equation E equals mc squared, where the other c here is the speed of light, different from the specific c here. So we want to see how much mass we can create from this energy gained by this lead brick. So from here we get the mass E over c squared, energy over speed of light squared. It's a very little gain, 10 to the minus 12, but it's there. These become very more explicit when we look at nuclear particles. Okay. Number 8 says photons of what minimum frequency are required to remove electrons from gold. So the work function of gold is given. So the photons have to have the frequency equivalent to the work function or greater. Okay. So there's no kinetic energy at this point. So the minimum frequency with the frequency corresponding to the work function. So work function plus kinetic energy equals the energy of the particle. So you first of all need to, heat up the electrons and then eject them. So the ability to heat them up and make the electrons ready to eject, that's work function. If you have energy more than the work function, you can now eject those electrons. So, and then give them kinetic energy. So work function plus kinetic energy is equals the energy of the light that is used to illuminate the photoelectric effect. But in this case, we're only discussing work function. We don't have any extra kinetic energy. So work function is H, Planck's constant times frequency. So kinetic energy is 0. Frequency is just work function over H. The work function is given 4.8 times electron volt. You convert to joules, multiplied by 1.6 times 10 to the power minus 19 joules is 1 electron volt, divided by the Planck's constant, and you get your answer in frequency right here. Then the other one now says when ultraviolet photons, number 9, with a wavelength of 3.45 times 10 to the negative 7 meters are directed at the surface of an unknown metal in vacuum, electrons with a maximum kinetic energy of 1.52 electron volt are emitted from the surface. What is the work function of the metal? So we are given kinetic energy now. So we are given the wavelength of this guy. So from this wavelength, we can calculate energy, HF, which is Hc over lambda. And that energy equals work function plus kinetic energy now, because we have the kinetic energy given. So Hc over lambda, work function is energy minus kinetic energy, which is HF minus kinetic energy. And HF is Hc over lambda minus kinetic energy. Well, if we're given the frequency, we can calculate the energy with HF, but we are given the wavelength. So frequency is C over lambda. So we just convert frequency to speed over wavelength. So Hc over lambda minus Ke, because we are given lambda, will give us the work function. So this is H times speed of light over lambda, 3.45 times 10 to the minus 7. That's given minus the kinetic energy given 1.52 electron volts. Don't forget to convert to joules in SI units. And then when you do the subtraction, and you get this in joules, but they have their answer in electron volts. So I divide again by 1.6 times 10 to the minus 19 to convert to electron volts. This becomes the correct answer in electron volts. Okay. That's number 9. We'll go straight to number 10. It says the work function for a particular metal is 4 electron volts. Which one of the following best describes the wavelength of the electromagnetic radiation needed to eject electrons from this metal? So we want to see, you want to eject electrons. So you have to have the work function at least or more to be able to eject electrons. So, work function plus kinetic energy is the energy of the light that's coming in. So work function plus kinetic energy equals HF, which is Hc over lambda. So Hc over lambda equals work function plus, we want to see the minimum energy you need to get to work function. So let's see the lambda corresponding to this work function of 4 electron volts. So Hc over work function is our lambda. And from here, we get the lambda to be this guy. So this is the wavelength you need. So the wavelength, if you increase your energy, your wavelength gets shorter. So you need the wavelength of this or a shorter wavelength, which means more energy, okay? If it was frequency, you need the frequency for the work function or a higher frequency because higher energies corresponds to higher frequencies because of the inverse relationships between frequency and wavelength. So a physicist wishes to produce electrons by shining light on the metal surface. The light source emits light with a wavelength of 450 nanometers. The table lists the only available metals and their work functions. Which metals can be used to produce electrons by the photoelectric effect? Okay. I think I had this twice. So this is the correct. So we've done this. So this one here, you see the solution here, the work function is what we need to see what energy can we get from this wavelength for the work function as the minimum energy you need to eject electrons and or higher. So that work function is given Hc over lambda, H times C. These are both constants. I put the lambda in here, 4 nanometers. I get 4.42 times 10 to the power minus 19 joules divided by 1.6 times 10 to the power minus 19 to get electron volts. It just gives me 4.4, about 1.6 times 10 to the power minus 19. Actually, I think I missed something here. I didn't divide, I just divided by 1 times 10 to the power minus 19. So it's actually supposed to be divided by 1.6 times 10 to the power minus 19. So let me do that on a calculator here online. So I'm doing 4.42 divided by 1.6. That gives me 2.76. So the correct answer here becomes 2.76 electron volts. 2.76 electron volts. So that's the work function here. So 2.76 electron volt, if I divide this by 1.6 times 10 to the power minus 19, that's the work function. So any of this, if we go to the next table now, anything that has 2.6 or less, this guy will be able to eject electrons from it. But anything that has more than that, he won't be able. So I only see barium and lithium. So barium and lithium are the only ones that are possible in this case. So the correct answer is D. So because I did it wrongly before, I had another one that could be possible because I didn't do the division correctly by 1.6. So only these two have energies less than 2.67 that we got from the 2.76. So 2.76, this is the work function of this guy. 2.76 is higher. So 2.76 will eject electrons with some kinetic energy after minusing the work function. 2.76 is greater than this guy. I have some, but 2.76 is less than this guy. So it will only eject electrons from barium and lithium. So the correct answer is D for this problem. So it's not 4.42, but 2.76 electron volt. Sorry about that. Now let's go to number 12. So what is the de Broglie wavelength of an electron, given the mass of an electron, 9.1 10 to the minus 31 kilograms in a 2.5 times 10 to the power 3 volt X-ray tube? So the de Broglie wavelength, the formula is known is the H over the momentum, Planck's constant over mass times velocity, which is the momentum. Then we have to do some calculations here to get velocity in terms of energy. So kinetic energy, half mv squared is energy. So from here, I solve for velocity is square root of 2e over m. So this is a V here, I put it for V in this case for H here. So the de Broglie wavelength becomes H over M instead of V, I have square root of 2E over M. The M goes in the bracket M to the 1 minus M to the times M to the minus half. So it becomes M to the half. I just want to put the M inside the square root here. So these two are basically the same thing, this side and this part. So I have the Broglie wavelength in terms of energy, but I'm giving the volt. This is the potential, the potential. And I know that the potential is work done per unit charge. So work done, which is electrical potential energy, is charge times the potential. So this energy here is the same as charge times potential. This charge is charge of an electron times the potential given in the X-ray tube here. So now I have everything I need. So my de Broglie wavelength, I successfully followed this whole substitution procedure and wrote it in terms of Planck's constant over the charge times the potential and the mass. All I need to do is substitute the values H 6.63 10 to the minus 34. So this is an equal sign here. And then divided by 2 times the mass of an electron times the charge of an electron times the voltage given here and the volts given here. And then when I do this, I get the answer correctly, 0.025 nanometers or 2.5 times 10 to the minus 11 meters. Okay. Don't forget the square root sign here, please. Okay. Question 13, each atom in the periodic table has a unique set of spectral lines. Which one of the following statements, you see right here, which one of the following statements, is the best explanation for this observation? So electrons and atoms are in constant motion. These things are all true, but which one of them relates to the spectral lines? Each atom has a unique set of energy levels. So when you excite an atom with a particular energy, it gets excited or de-excite and release that same amount of energy. So spectral lines are related to the energy levels of the electron, not this other reason. So D is the correct answer for this particular one. Number 14, which one of the following will result in an electron transition from n equals 4 level to n equals 7 level in hydrogen atom? For the hydrogen atom, we know any energy level is given by negative 13.6 electron volt over n squared. So from the 4th to the 7th, the difference in energy levels is putting 7 here minus putting 4 for n. So minus 13.6 electron volt over 7 squared minus 13.6 electron volt over 4 squared. So this minus becomes plus, minus 13.6 over 7 squared plus 13.6 over 4 squared. I do this here easily, 16 and 49, and then I get 0.57. Whatever answer I get here will be in electron volts. That's why I left the unit there. So when you go from lower energy level to high energy level, you are excited. You get, it means you have absorbed some light. You got some light. Somebody gave you some money. You're excited. You jump up. And when you de-excite, you have low energy. You de-excite from higher to low energy. You are sad. You give off that light. So this must be an absorption to go from the 4th energy level to the 7th energy level for sure. Okay. In which of the following sets do the species have the same neutron number? So this is the explanation. The top here is mass number, the bottom is proton, and the difference is the the number of neutrons, because proton plus neutron is what gives you the mass number. So mass number minus proton number will give you neutron number. So 16 minus 8, is it the same as 23 minus 11? 16 minus 8 is the same as 14 minus 7. So you keep checking which of them gives the difference that are equal, and the only correct answer here is C. 14 minus 7 is 7, 13 minus 6 is 7. So these are the two that have the same neutron numbers. The rest don't have the same neutron numbers. Okay. Number 16, it says, this question refers to the figure shown. Which one of the following concepts explain why heavy nuclei do not follow the n equals z line? They do not, because for n greater than z, you're going to see that the Coulomb electrostatic repulsion becomes important for large that. So this is due to Coulomb's repulsion when you have n, high n and greater than z in this case. So you see n is longer and z is shorter. Well, when they were symmetric, n equals z, then you can have no much Coulombic repulsion phenomenon. Okay, so this trend is due to when n is higher than z, we have this deviation because of the Coulomb repulsion in the nucleus of the atom. Okay, so it's like the protons are repelling each other within the neutron in the nucleus, basically. What is the mass defect of 120 and 50? So the mass number is 120, the proton number is 50. So we want to see the mass defect. So we are given the atomic mass, so we're going to calculate the real mass. So the proton number is 50, the neutron number is 120 minus 50, which is 70. So we're going to multiply the proton number by the atomic mass of proton, which is the atomic mass of hydrogen. And then we're going to multiply the neutron number, which is 70, by the neutron atomic mass, 1.0867. So the calculated mass will be 50 for protons times the hydrogen mass plus 70 for neutrons times the neutron mass. This is what we calculate. But what we actually measure is this guy. So the mass defect is what we calculate minus what we measure. And that just gives us this, this mass defect here. And you multiply by 1.6 times 10 to the power minus 27 for the mass of the proton to get, because U is mass of proton, to now get your answer in kilograms. After taking the difference for U, becomes this answer in kilograms right here. Okay. The next one says the half-life of a particular isotope of iodine is 8 days. How much of a 10-gram sample of this isotope will remain after 30 days? So we are given the half-life. This is the decay and disintegration constant, lambda here, the time. For half-life, when we put T to be tau, NT goes to N over 2. So when you calculate this, you get lambda to be ln 2 over the half-life when N cancel N, you take the log of both sides, and then to remove the this exponential here. Okay, so you get ln 2 over tau to be the lambda. So tau is your half-life. So your lambda, your disintegration constant, becomes ln 2 over 8, because 8 days is given the half-life, and we get our lambda. And then now for 30 days disintegration after 30 days, so it will be 10 exponential minus lambda times 30 days, and then we are given the initial amount to be 10, and then we just get that. So the target here is to first of all find lambda using the half-life, and then substitute to get the disintegration after 30 days after starting with 10 grams. So we're going to see 0.7 gram, 74 grams disintegrated after 30 days. Question 19 says the ratio of the abundance of carbon-14 to carbon-12 in a sample of dead wood is 1/4. The ratio for living wood. Okay, so we can get that now, that NT is N0 over 4, 1/4 for living wood. If the half-life of carbon-14 is 5730 years, also from the half-life, we can get lambda to be ln 2 over half-life. And then they're asking us to find how many years ago did wood die. So we're looking for the time. So from here, time, from this equation, if you solve for time, is 1 over lambda ln N0 over NT. Now I'll put NT to be N0 over 4 here. So it's N0 divided by N0 over 4 for this part. And lambda is ln 2 over tau. So 1 over lambda becomes tau over ln 2. So tau over ln 2 ln N0 over NT. This is the half-life tau over ln 2 ln N0 divided by NT, N0 over 4. N0, this becomes times 4 over N0. So N0 cancel. I have ln 4 over ln 2 times this guy. Ln 4 over ln 2 just gives you 2. So it's just 2 times the original half-life we're given. It's just given times that in years. And the answer is given in this form, 2 times 5730. That's the correct answer here. Now we have very close to the last problems here. The next one, number 20, say consider the nuclear reaction. So it means this plus X equals D plus I. So the symbol D indicates the deuterium nucleus, which is this. So this, you write the reaction. This plus X gives I plus deuterium, which is this guy. So we want to make sure that the mass number balances on both sides. So 124 plus 2 is 126. So we only have 122, so we want to make it 126, so we need 4. M has to be 4. And here also the proton numbers have to balance. So here is 53, here is 154, here is 52. So we need 2 here to make 54 on this side. So it's 4 and 2. So we know this is number of protons. 4 minus 2 will give us number of neutrons. So X must contain 2 neutrons, and X is actually a helium nucleus, basically in this case. So that's the correct answer. What is the importance of thermal neutrons in nuclear processes? So what they do is capture results in uranium fission. That's the use we use thermal neutrons in nuclear processes. Basically, they are not necessary for fusion, only in in uranium fission when we break uranium. So the correct answer for this is A for 21. And this is just a quick review to help you. I know you might do your own reading and deduction, but this is just to guide you in case you are confused about a certain thing. And I hope this helps you. I'm going to stop here for today, and you guys have a good semester and have a good final. I wish you guys a good luck in your exams, and bye for now.